Problem number 5, Fall 2011, Exam 4. We have a cart with a given mass, and this cart we're going to factor in its rotating wheels, four of them, each with another given mass, a radius of the wheels, and the mass moment of the wheels, mass moment of inertia of the wheels is given. Cart starts from rest, rolls down a curved track, and an elevation drop. Determine the speed of the cart at the bottom of the track. Okay, when we did this in Module 3, all we did was factor in the initial potential energy being equal to the final translational kinetic energy. Now we've learned about rotational energy, we'll have to factor that in as well. So let me write it first like this. Conservation of energy says that my initial potential energy is going to be my final kinetic energy. Okay, but final kinetic energy is going to have two different parts. So we're initially at rest, so we'll have mgh here, but this kinetic energy is going to have a 1/2 mass velocity squared term, and it's going to have a 1/2 I omega squared term for the wheels. Okay, and this is our final velocities. Okay, potential energy is easy. We have the mass of the cart. Now this is a hint here, excluding wheels, we're going to have to factor in the wheels because they're also translating as well as rotating. Alright, so we're going to write our mass as 0.5 plus 4 times 0.08. Okay, so that's our total mass in kilograms. G, of course, is 9.81. And H. So if we draw our track here, here's our block initially, here's our block initially, set a datum. Right there, it says it drops 0.2 meters. So there's our initial H. Okay. And we'll go ahead and calculate this term because I'm going to need it again. Okay, 4 times 8 is 32, so that's 0.32 plus 0.5, that's 0.82 kilograms. Okay. So this term was our entire initial potential energy. Our final potential energy is going to be the translational part, 0 times 0.82 kilograms, 1/2 times 0.82 kilograms times what we're trying to find, the final speed. Okay, so there's my translational portion, 1/2 I omega squared. Okay, I have got 4 wheels. Okay, so there's the 4 wheels. Okay, and each one has 1/2 moment of inertia, 1.5 times 10 to the -4th. So 1.5 times 10 to the -4th kilogram meter squared. Okay, so here's 4 wheels, the 1/2 from the rotational kinetic energy equation. Here's my I. Omega squared is going to be, or omega is going to be related to the velocity by the radius of the wheels. Alright, so I'm going to put V2 over radius of the wheels was 0.6. Oh, let's see, I'm running out of room here. That's going to be meters, and this whole quantity is going to be squared. Alright, so the meters will get squared here, we'll cancel out that, and we'll end up with kilograms mass and velocity squared units, which is work or energy. Alright, so we have a single equation here. Has v squared in this term, v squared in this term. We'll just combine and solve. I'll use the solver to do that, so I can check all my work. Okay, so I'm going to get into the solver, clear everything out. I will move this to the other side, so makes negative 0.82 times 9.81 times 0.2, so double check that, plus 0.5 times 0.82 times, I'll use x for my velocity, unknown, squared. Okay, plus 4 times 0.5 times 1.5 times 10 to the minus fourth. So I'll do that like that. Okay, and I'll have an x squared term divided by 0.06 squared. I could have put both of those in parentheses and squared the quantity. I just squared each individual term. Alright, I believe that'll do it. Initial guess, let's go 5 meters per second. Initial guess, and the actual answer is 1.8. 1.81. Okay. My units are consistent. Everything's in kilograms, meters squared, second squared. Okay, so my final answer is V2 equals 1.81 meters per second. Key points on this problem: first, identify conservation of energy, then remember to incorporate the rotational energy of the wheels. Okay, if we did not do that, then this whole second term would be 0. Okay, it's an easier problem, but we get a different answer.